Hi, this is Steve with iFLOW. Welcome to our video series. In this segment, we're going to look at modulation. We're going to look at variable speed modulation as it relates to HVAC equipment. Perhaps it's a term that you've heard. We're going to try and relate it to, or make it easy to understand what we're referring to, and then how it applies to HVAC equipment. So first, full modulation. Your car is a great example of full modulation. When you push on the accelerator, RPMs go up, speed increases. When you take your foot off the accelerator, RPMs go down, speed goes down. You can go from 5 miles an hour to 50 miles an hour and anywhere in between, depending on the traffic, right? If you're on the highway and you've got no traffic, you can ramp up to 50, 60 miles an hour. If you're in the city at rush hour, you're going to be bumper to bumper and you need to be able to go a little bit and off and adjust. So your car can adjust to that depending on the signal that you give it based on the push of the accelerator on and off the accelerator. So that's variable speed modulation. You got full variability to increase or decrease the speed. Can you imagine driving though, and let's make it worse, driving in traffic with only two conditions, two speeds. Let's say 60 miles an hour or off. So it's either full on or stopped. I would suggest that's probably pretty hard to do. Right, 60 off, you wouldn't get too far, you'd be going crazy, likely getting an accident. Well, that's unfortunately how your furnace is operating in most of the homes in North America. So full modulation means comfort. So just as you want a smooth car ride, you want a smooth and comfortable temperature in your home and consistent throughout. But unfortunately, the majority of heating and cooling equipment are only single stage. And what that single stage means is when the thermostat calls, it can only operate at one speed, and that's the maximum. So again, relating back to the car, it can only drive at 60 miles an hour or off. So let's say a typical furnace, 60,000 BTUs or off. If you only need 20 miles an hour or 20,000 BTUs, the furnace can't do that. It's 60 miles an hour or 60,000 BTUs or off. So that's unfortunately single stage, and that results in cycling. And every time the furnace cycles, you lose efficiency in that you've had to heat up your heat exchanger, and then when you cycle off, you deliver all of that, you have to post-purge all of that heat out of the heat exchanger. There is two-stage equipment now on the market, and it's been in the market for a number of years, but it's only marginally better. If you think about the car example, two-stage are usually on a two-stage unit. You have 100%, and then stage one is at 70%. So it gives us one extra speed, but we need more than one extra speed in our opinion. So let's again relate it to the car. So let's say your car can go 60 miles an hour or off. That's a single stage unit. With a two-stage unit, now we have one more speed at 70% of that. So 60% or 70% of 60 miles an hour, for example, would be 42 miles an hour. So we can go at 0, 42 miles an hour, or 60 miles an hour. And those are the only choices we have. That's two-stage equipment. So even though it may sound better, it really isn't better. Or it's marginally better. It really doesn't help in the efficiency. And we really have to look at where that 70% number falls in terms of BTUs to see if it's of any value in your home based on the heat loss of your home. So what does that mean? So we're looking at cycling. So if I can only drive it at 60 miles an hour or off, or if we relate it to the furnace at 60,000 BTUs or off, how is that going to work in the home? So let's say, and I'm looking at a heat distribution up here in the corner. I'm looking at most of my heat distribution. This is a 60,000 BTU furnace installed in a 1,600 square foot home in 5 different locations across the US. The blue line being Madison, Wisconsin, the orange line being Albany, New York, the gray being Portland, Oregon, the yellow being LA, Los Angeles, California, and then the green being Birmingham, Alabama. So we have these 5 locations, and this is the heat distribution. So how many thousand of BTUs is it using? What percentage is it using through the heating cycle? And you see here that the most used period, both for Madison and Albany, New York. So we're looking at the heating side predominantly, but also in Birmingham and in Portland. This is the biggest distribution. This is 20% of the load. 20% of 60,000 BTUs is 12,000 BTUs. So what this is saying is the majority of this distribution is 12,000 BTUs worth of heat required. And our furnace is at 60. So think of it, relating again to speed. What this is saying is, hey, you only need to drive 12 miles an hour. Why are you driving 60 miles an hour? Or if you only need to drive 12 miles in an hour, but your car can only go 60 miles an hour, then you have to drive it very quickly, and then you'll get to your destination quite quickly, and then you have to stop. So this is what I'm kind of looking at in this unit. So if we have to run 12,000 BTUs, but I have a single stage furnace that runs at 60,000 and only need 12,000, I'm going to be running for 1/5 of the time. Right? So I'm going to be on for 1 minute, then off for 4. And I'm going to do that 12 times an hour. Or I'm going to be on for 4 minutes, off for 16 minutes, and I'm going to do that 3 times an hour. So because I can't, if I was to run, like the ideal, if I have to run 12 miles an hour, if I need 12 miles an hour in my car, I'm just going to set the cruise control at 12 miles an hour, and I know in 1 hour I'll be there, and it'll just be a nice, smooth, comfortable ride. Right? In this case, I can't do that. I have to set it at, well, I know I can only drive 60 miles an hour, so if I do that for any length of time, I'll get there too quickly. So I'm going to drive at 60 miles an hour for 4 minutes, and then I'm going to stop for 16, and then I'm going to drive for another 4, stop for 16, drive for another 4, and then I'll be at my destination. With 2-stage unit, I'm a little better. I'm going to run now for almost 6 minutes, and then I'll be off for about 14, and I'm going to do that 3 times an hour. So my run time has gone from 4 minutes now to 6 minutes with the 2-stage, and then with a fully modulating furnace with a minimum input of 40,000 BTUs, now I'm going to be a little better. I'm going to run for 15, and I'm going to be off for 15. Run for 15, off for 15. So this is 1 to 1 to 1. So this is better, but still cycling, 3 times an hour, 4 times an hour. This is cycling 6 times an hour. But the run time, so the run time is very short, and we lengthen it up. So when you have a short run time, what that means is you're delivering 60,000 BTUs in that 4 minutes. So you're full on, you're delivering lots of heat into the house very quickly. And then you're going to satisfy the thermostat very quickly. If it ran for too long, you're going to overheat the space. So we run for 4 minutes at maximum, and then we put the brakes on, we stop. All of the heat that was developed in the heat exchanger has to be post-purged out, so you send all of that heat out, and your efficiency drops. So the more you cycle, the worse the situation gets, and that's why the less cycling, the better the efficiency. But the key is here in this distribution. So we have to match, we want to match not only the maximum input, but the minimum input for your home, and match the appliance that best meets those 2 criteria, and that will be the best performing solution. So you wouldn't put up with that type of car on the road, right? They can only do 2 speeds full on or off. So why would you put up with it at home? Your home is your biggest investment by far. In a recent survey by Emerson, as I mentioned, nearly 40% of the homeowners admitted to having disagreements about uncomfortable temperatures in their home. So the heating and cooling equipment in your home, they determine your day-to-day comfort. Right? That's the HVAC equipment is going to determine how comfortable you are in your home. So if you've just purchased a $600,000, $700,000, $800,000 home, or even a $200,000 home, there's no need to be uncomfortable. You can be fully comfortable, and you should be in your home because you spend 69% of your time in your home. Your health, when we talk about HVAC, the V is the ventilation side, most of the time ignored, unfortunately, by the industry, but that's part and parcel of it. And then the operational cost. So your HVAC system not only determines your comfort, but also the operational cost. So how much it's going to cost you every month to run your system, whether it's your AC system or your heating system, that is determined by your HVAC equipment. So it has a significant impact not only on your budget, your monthly budget, but then your comfort. So so make sure that we're sizing this properly. Make sure that when your contractor is talking about modulation, that you know that it's both minimum and maximum that you need to meet. So we can do it better. So again, by decoupling those functions, we can allow the industry to select the best cooling equipment, the best heating equipment at the conversion, and then we can take that heat and cool into the iFLOW, and then we distribute it through the system. So again, choose a heating system that matches the maximum, but also the very low minimum input that your smallest zone has, and then a high turn down ratio. So we'll talk about turn down ratio. The ratio is just the ratio of the maximum input divided by the minimum input. So if I have a 200,000 BTU unit with a 10-to-1 turn down, 200,000 divided by 10-to-1 turn down. So, or if I have a maximum input of 200,000 and a minimum input of 20,000, for example, 200,000 divided by 20,000 is 10. So this unit would have what we call a 10-to-1 turn down ratio. The higher the turn down ratio, the better the ability of that unit to modulate. So on the cooling side, you want an inverter driven if you can. So again, a single stage or two stage will be cycling. On the electric side, there's not as much loss on the cycling side, but you have the issue if your equipment is oversized, then you're going to have issues with freezing your coil. When you get into, when you're delivering, let's say, too much refrigerant to the coil, or if it can only deliver at maximum, or let's say two stage at 70%, it's going to deliver that refrigerant in. If you don't have the air volume going across that evaporator coil, it's going to start to freeze up. And then before it freezes up, it goes into defrost mode. So then you're in defrost mode. What it means is your equipment's running longer than it needs to. So really there's going to be additional cost if your equipment is oversized. So it's not going to function properly, or as best optimally, let's say. It's not going to run optimally, and it's going to cost you more. So there is an incentive to go with an inverter driven system. So an inverter driven system, whether it's an AC unit or heat pump, will be fully modulating. And then we take that modulation capability on the AC side, pair it with our modulation capability on the iFLOW side, and we can deliver. So if we have one zone that only needs 150 CFM, so very, very small, a very, very small load, we can do that. We can do that. You know, let's say 4,000, 5,000 BTUs in a certain area. We can deliver that with an inverter and with the iFLOW. So when we look at equipment out there and we start selecting the heat sources, so this is on the gas side, we're going to look at this turn down ratio. And again, the turn down is just the maximum divided by the minimum. So the maximum input divided by the minimum input, and that gives us our turn down. So we're looking at something with a high turn down. So if we look at the existing furnaces in the market, so a single stage furnace has a turn down of 1. Basically it's on or off only. Our two-stage furnace is a little better. It's on at stage 1, then stage 2, and then off. So again, stage 2 is stage 1 is normally 70%, then 100%, then off. And then we have a modulating furnace, and those Turn down ratios are often 2.5 to 3. Let's say they can modulate down to 35 or 40%. And those efficiencies are good. But if you look at the minimum input, so if I have a 60,000 BTU furnace, for example, so these are all 60,000 BTUs. So if I have a 60,000 BTU furnace that's coming on only as a turn down of 1, that means it's coming on and off. My minimum input is 60,000 BTUs. So if my heat load is anything less than 60,000 BTUs, the furnace is going to be cycling. Typically that'll happen in the shoulder seasons, you know, in September and October, where I need a little bit of heat, I don't need it full on. That's when it's going to be cycling worst. The two-stage unit, again, a little bit better, but its minimum input, again, looking at a 60,000 BTU furnace with stage 1 at 70%, 42,000 BTUs is my minimum input. So again, still quite high compared to many of the houses today. If I get into modulating condensing furnaces, now I'm 2.5 to almost 3 to 1, or sorry, yeah, turn down ratio of 2.5 to 1 or almost 3 to 1. I can modulate down to kind of 35 or 40%. Efficiency is decent, but my minimum input is still quite high at 24,000 BTUs or 23,000 BTUs, depending on the model. So you want, if my heat load, you know, if my heat load is above 24,000, this furnace would be a great option. If my heat load is above 42,000, this furnace could be a great option. If my heat load is at 60,000, this would be a great furnace. But if it's anything other than those, these units will not perform very well, unfortunately. So then we look at, okay, what are our options? Are there other appliances that may work better in certain applications? So now we look at a gas-fired water heater. Has a turn-down ratio of 1, so it's basically on or off. Efficiencies are quite low, so efficiencies 62 and kind of up from there. We typically, the inputs are typically 35 to 100,000 BTUs. We typically wouldn't use a gas-fired unit, especially when the efficiencies are this low. You wouldn't want to run your heating all winter long at this efficiency. This would be this wouldn't be good for your expenses, nor for the environment. So we would kind of disregard this until we get into these higher numbers. If that's a higher number and we're not cycling, there could be some cases where we would look at this unit. When we get into fully modulating condensing combi boilers, so ModCon is modulating condensing. So ModCon combi boilers, 10 to 1 turn down, can modulate to 10% of its input. Inputs are usually 110 to 200,000, so the minimum input will be 11,000 to 20,000. So again, not bad. This is much better than a 42,000 BTU furnace. That'd be a two-stage furnace with 95% efficiency. This would work 95% at 11,000 BTUs, so much better option if my heat loads are, you know, 11,000 BTUs or more. So let's take another look. So now we get into the modulating condensing tankless. So with these units, I get a little bit better. So now I'm 13 to 1. I know there are units coming to market that will be 15 to 1 soon enough. So that takes us down to 7.5% of the total input. Efficiencies are very good at 95 to 98%. And I can get as low as, let's say, 9,000 BTUs. So 9,000 to 15, kind of in that range on the minimum input of the tankless. So if my heat load is 12,000 BTUs, then this would be a perfect unit for that. If it's 9,000 BTUs, I could find a unit that would work very well in that application. Let's look now at modulating condensing boilers. Often have a 10 to 1 ratio now. Usually AFUEs of 95% or better. I can get a 50 or 60,000 BTU boiler with an 8 to 1 or 10 to 1 turn down ratio. I can find a boiler that has a 6 or 7,000 BTU input. So now I can actually match this boiler that's going to give me great efficiency at very low part loads and pair it with the iFLOW and get a great combination system. Much better than running at even the best modulating furnace that has a stated AFUE of 96 but can't go below 24. Below 24,000 BTUs, if this furnace was tried to run at 6,000 BTUs, it would be cycling all day long, and the efficiency definitely wouldn't be 96 to 98. So if I compare this boiler with this 95% AFUE running at 6,000 BTUs and put it into an application, let's say, that had a minimum input of 8,000 BTUs, that would be a great option. A great option, much better option than this. Better performance, better comfort, better all around. So this is the heating equipment and the modulation. So here's an example. So we have a 2-story, 1,400 square foot home. It's designed, it's a single detached home, built to Energy Star for new requirements, so built very well. Energy Star is about 20% better than standard building code. And here are our loads. So we have a heating load of 23,000 BTUs, and we have a cooling load of 16,600. So 1.5 tons of cooling, 23,000 BTUs of heating. But we're going to zone this house. So this house is zoned, and as such they've divvied up the heat loss into different zones. So on the heating side, we'll have 7,000 BTUs on the top floor, almost 8,000 BTUs on the main floor, and 8,000 BTUs in the basement, for a total load of 23,000 BTUs. On the cooling side, 7,000 BTUs in the top floor, almost 7,000 on the ground, and then because we don't have to cool the basement as much in the summer, because it's already going to get naturally cool, only 3,000 BTUs required in the summer on the cooling side. So we take these numbers and then we calculate the CFM required. Look at the CFM rates. So we need only 444 at total on the heating side, and then divide it up into 142, 146, so almost 150 CFM per zone. On the cooling side, 555 CFM, 230. So typically this would be very, very difficult to do, right? Many of the units have a minimum CFM of 400 or 500 CFM that they need to blow into that system. So that 4 or 5, that's maximum. So if I'm zoning this, there's no way I can effectively zone that. I'd have to run a bypass with all of the furnaces in the market at this point, for the most part. But with iFLOW, for example, we can do that. We can pair, if I have this heat load, for example, 6,000 or 7,000 BTUs, what if I pair it with this boiler? So I pair it with this boiler that has a minimum input of 7,000 BTUs. I need 7,000 BTUs, 7,000, 7,000, 8,000. So perfect to do on the heating side. I can put this boiler in, 95% AFUE, or 94% on this one, sorry. I can run it that heat load. I can just tie it in. Perfect application. I can set this blower to run at 150 CFM without problem. I get a great, comfortable solution. Every floor is going to be comfortable. Every floor is going to have the CFM. They're not going to hear any noise from excessive air coming through. It's not going to be too hot, too cold. Perfect application. So this is what we're talking about when we're matching not only the maximum but the minimum heat loss as well. On the cooling side, again, we're not getting a lot of losses, but to be able to deal with those same small loads, we want to make sure that the AC system isn't too oversized, because then we'll get a lot of defrost cycling issues. So single stage unit 1, it's on off at 100%. We have a 2-stage unit, again the same turn down ratio. It's on off, or it's usually 70% or 100%. The inverter driven, let's say a 5-stage unit, so if it's 5, it's going to run in 1/5, so 100%, 80, 60, 40, and then 20%. So 20% would be the minimum input. And then we have almost the full inverter driven units that modulate down to about 15%, so almost a 7-to-1 turn down. That's a great option for us. So if we can go back to this system, so we need 1.5 tons, and I don't know if I have, let's see if I have a, yep. So, so let's look at this example. So now we have this, let's say we have a cooling load of 30,000 BTUs divided into these floors. So we need 1 ton, 1 ton, and half a ton for 2.5 tons of total cooling, 400, 400, and 200 CFM for a total of 700 CFM. So typically if I set my 2.5 tons with a 2-stage unit, stage 1 would be at 70%, which is at 700 CFM. Stage 2 would be at 100%, or 1000 CFM, because that's my total CFM required. Now, if I'm zoning, and again, zoning for maximum comfort, and so we don't freeze the coil and have to go into defrost mode all the time, we want to be able to deliver into that top floor only 400 CFM, only the CFM that's required. Can we do it with this unit? No, we can't. So we need an inverter-driven system that can modulate down to this 400 CFM. So 400 would be 40%, and as we saw, can we do 40%? Absolutely. We can do 40% with the 5-stage unit without problem, no cycling. We can run the inverter. The inverter will just run continuously and give you great efficiency, great performance, and no freeze-up issues in the home. So for the contractors, they can't reduce the CFM as we saw. If they reduce the CFM, they risk the coil freeze up. So they have to bleed the excess CFM. So what I'm mentioning here is this 700 CFM that the minimum is at. We only need 400. So what they're going to have to do is they can't reduce the CFM because it's a 2-stage unit. So they have to run a bypass, and that bypass means that they'll be delivering the 700 CFM out. Well, I only need 400 CFM, so that other CFM is going to, right, the other 600 or the 300 CFM is going to come back here and be cycled around and around and around again. So, as I mentioned, the inverter system is going to be the best solution for that. If we go back to that, okay, just continue on. So, the inverter, so what this inverter does, this 2-stage, this will be our single-stage AC unit, this green line. So no modulation, basically on or off based on the thermostat call. With our 2-stage unit, we're going to be a little bit better. We're not going to cycle, we're not going to see the temperature variation as wide because we can hit 70% rather than 100%. So we're going to come on and off and on and off at less variability. With the inverter, we're going to be following the temperature in the room very, very precisely, in that we're able to modulate to whatever BTUs they need in the space. So that's again the advantage of modulation. So with regards to modulation and how the iFLOW works with modulation, and again that's our theme for this whole section is modulation, the advantage of modulation, the effects of modulation. And then now, how do we work? How does the iFLOW work with modulating units? So, so the inverter modulation works with the iFLOW in this way. Let's say we have these zone designs. We have zone 1, zone 2, zone 3. Let's say 400, 400, and 200 CFM. So as we deliver 400 CFM, let's say only zone 1 is calling. We're going to be delivering, the blower is going to ramp up for 400 CFM and deliver 400 CFM through zone 1. Not a problem. As we deliver that volume of air, that 400 CFM across the evaporator, the temperature of the refrigerant within the evaporator is going to change. The pressure is going to change, and then as that pressure goes back to the compressor is going to see that and it's going to be able to modulate. Then as, let's say, zone 2 opens up, we need another 400. So now we need 400, 400, now we need 800 CFM. So the blower is going to ramp up to 800 CFM, run the 800 CFM now across the coil. This is going to warm up that coil even more, right? Because we're cooling more air. So the refrigerant is going to warm up as it's cooling that more air. That refrigerant going back at a warmer temperature, at a different gas pressure, is going to allow the compressor to modulate to whatever we're going through. So as we modulate the airflow through the house, depending on the number of zones that are calling, the compressor for the inverter unit will modulate the inverter based on the pressure differential that we're creating across the evaporator coil. So back to the point at hand, it was modulation. We were talking about modulation. So we don't advocate for one source over another. We can work with any of the heat sources. But what we do advocate is to match the source equipment and the modulation range of that source equipment to both the maximum and the minimum inputs. When we do that, then when we pair that with the iFLOW to deliver the minimum and maximum, and then zone it to deliver that to the exact place in your house, so when you need it, where you need it, and in the exact amounts you need it, that's going to be the optimal efficiency and comfort for the homeowner and maximum efficiency. So the closer to full modulation, the better performance of the combi system, the better efficiency of the combi system. So to provide that best option for the homeowners, we need to select the best equipment for the application. And that's why we believe being able to separate the three functions of the HVAC equipment allows the industry to create the best solutions in the market. So we know there are better solutions. So again, thank you for your time. I hope it's been helpful. If you have any questions, by all means you can reach us on our website at iflowhvac.com, or reach out to me, Bagshaw Steven, at iflowhvac.com, and that's steve.bagshaw at iflowhvac.com, toll free or myself. So by all means, we'd love to hear your feedback. Feel free to reach out. Again, hope you found it of value. Thank you for spending some time with us.